All right, might as well make this lecture, since nobody wanted to come to my office hours, I'll start lecturing. Cool, it's okay. This is first derivatives and their graphs. So we will be graphing functions based on the characteristics from the first derivative. Theorem 1, increasing and decreasing functions. If the derivative is positive on some interval AB, then the original function will increase from left to right. This means it'll increase all the way from left to right. If the derivative is negative on the interval AB, then the original function will decrease as the graph falls from left to right. So remember that the derivative is just slope. So, turn the fan off, that's annoying. Okay, the derivative is just the slope. So if the derivative is positive, slope's increasing. Derivative is negative, slope's decreasing. And examples of that are, well, for a graph for a derivative to be positive and you increase, you can look something like that, like this, or like that. Those are all examples of an increasing function. If we decrease, well, just flip everything over. Decrease, decrease, and decrease. So those would be the examples of the graph. Okay, let's move. Okay. Example 1. Find intervals on which a function is increasing or decreasing. Given the function 8x minus x squared, which values of x correspond to horizontal tangent lines? So if you ever ask the question, where can you find horizontal tangent lines? Well, all you have to do is take the derivative, set it equal to 0, and solve for x. And the reason we set it equal to 0, because if I were to show you a horizontal line, what is the slope of all horizontal lines? The slope of all horizontal lines is 0. So if it says, which values of x correspond to horizontal tangent lines? Well, we're looking for a line whose slope is 0. So this means that take the derivative, set it equal to 0 because the slope is 0, because it's a horizontal tangent line, and solve for x. That's it. Make it sound easy, right? Okay. Right here in A. I think writing in blue, whatever. Okay, so the first step is take the derivative. We get 8 minus 2x. There's the derivative. The next step is get the derivative and set it equal to 0, because the slope of a horizontal tangent line is 0. So you take 8 minus 2x and set it equal to 0. Now solve for x. I'll move the 2 over, so I get 8 equal to 2x. And then I'll divide by 2. And x is going to equal 4. Okay. So when x is 4, a horizontal tangent line will exist on the original function when x is 4. So that's what we have found. Okay. So also what we have found is that this number 4 now becomes a partition number. It is a partition number. It also has another word for it. It is called a critical number. Okay. So any values found after setting the first derivative equals 0 and solving for x, these values are called critical numbers and or partition numbers. And the reason they're called partition numbers is because we come to the next problem. It says, for which values of x is the original function increasing and decreasing? So what this says to do is create a sign chart for the first derivative. This sign chart will tell us where the original function is increasing and decreasing. And to create our number line, we plot the number we found above. We plot the partition number, the critical number. So I create my number line. And I plot my critical number of 4. And now I have two intervals. Here's negative infinity. Here's infinity. My intervals go from negative infinity to 4, and then 4 to infinity. Okay. So this is a sign chart for the first derivative to tell us where the original function will increase or decrease. So now, what we do is we pick test numbers in between each interval. So, whoops, a little smaller. There we go. So now pick test numbers. And now, from negative infinity to 4, we can pick any number we want. And the easiest number to pick in there should be 0. And now from 4 to infinity, we can pick any number we want. And the easiest number to pick there is going to be 5. Now, take these numbers and plug into the derivative f prime of x. So I have f prime of 0 and f prime of 5. F prime of 0 and f prime of 5. So we're plugging it into the derivative we found above, 8 minus 2x. So 8 minus 2 times 0 gives me 8. And 8 minus 2 times 5 gives me negative 2. Okay, so with the sign chart, I don't really care about what the numbers are at the output. I only care about the signs of the output. So this 8 is positive, which means that, look at the sign chart, from negative infinity to 4, since any test number we pick, the first derivative will be positive. This means that the original function will be, well, the first derivative is positive, which means the original function will increase. All right, and then the next output is a negative 2. Again, I don't care about the number, I just care about the sign. So this means that any number we pick from 4 to infinity, the first derivative will be negative, which means the original function will be decreasing. Okay, so from negative infinity to 4, the original function increases. From 4 to infinity, the original function decreases. All right. So I guess I could write that down. F of x, not f prime. F of x increase on negative infinity to 4. And f of x decrease on 4 to infinity. That's all based on the sign chart above. Okay, now we want to sketch the original function just using the characteristics of the first derivative. So original function was f of x equals 8x minus x squared. I'm going to write that down. Okay, but I do want, it's a sketch, but I do want to see how much information I can pull from the original function. So here I'm just going to look for an X-intercept. And we know with X-intercepts, we let Y equals 0. We let f of x equal 0. So this means I take 8x minus x squared, set it equal to 0, and I solve for x. Here I can take a negative x out, and that leaves me with x minus 8 equal to 0. And it's factored, so I set these equal to 0. I should get negative x equals 0. X minus 8 equal to 0. Therefore, x equals 0, and x equals 8. These are my X-intercepts. And only get these if they're easy to find. This one was pretty easy to find. So I have an X-intercept at 0, 0. I have an X-intercept at 8, 0. Okay, now let's plot. So I'm going to plot my X values that I have, that I just found, my X-intercepts. So here's 0. Oops, make that bigger. Here's 0, 0, and then 1, 2, 3, 4, 5, 6, 7, 8. There's 8, 0. And then I'm going to plot, I'm just going to write the interval for my critical number. So 1, 2, 3, 4. So I'm going to write it on the interval. Okay. So now, all we're going to do now is sketch. So let's look at the above number line. This says from negative infinity to 4, the original function is going to increase. So coming down here, from negative infinity to 4, this function is going to increase right there. And then from 4 to infinity, the original function is going to decrease. So, decrease. And that's it. This part here represents my derivative increasing. So all of this means f prime is increasing. And all of this means f prime is decreasing. Yeah. There you go. F prime decrease. So if the derivative is increasing, this means the original function is going to increase from left to right. And then if it decreases, this means the original function will fall from left to right. And that's our sketch. Okay. Next. So we've seen sign charts before. That is the sign. We did that in the first exam, and that just destroyed everybody, which is cool. Hang on. Okay, cool. So we've done sign charts before. So now here we're doing them for first derivatives. So this is everything we've done already. So everything I'm about to read is everything we've done on the last problem. It's the definition of critical numbers. A real number x in the domain of f such that the derivative is equal to 0 or the derivative does not exist is called a critical number of f. So that's everything we did in the last problem. That means set the derivative equal to 0, solve for x, whatever value you get is called a critical number. And sometimes, depending on the function, the critical number you find may not exist for the derivative, but it could exist for the original function. or the other way around. It could not exist. It could exist for the derivative, but it may not exist for the original function. I don't think we'll be getting those type of critical numbers in this class. Okay. The critical numbers of f belong to the domain of f and are partition numbers for the derivative. We've done that already. When I say partition numbers, I mean it breaks up the number line. We made a number line. I put the critical number down, and it broke up the number line. The first derivative may have partition numbers that do not belong to the domain of f, so they are not critical numbers of f. That's what I just said. So critical numbers you find may not fit into the domain of the original function. And that's it. Yeah. But again, I don't think we'll get those type of problems. All right. Example 2, we're going to do the same thing that we did in the last problem. Find the critical numbers of f, the intervals on which f is increasing, and those on which f is decreasing for 1 plus x cubed. So find the partition numbers, find the critical numbers. It's the easiest step you can do to find critical numbers or partition numbers. Take the first derivative, set it equal to 0, solve for x. That's as easy as it can get. So that's number 1. Let's do that. So f prime of x is just going to be 3x squared. So 1 plus x cubed, that derivative is 3x squared. Then set the derivative equal to 0. 3x squared equals 0. Divide by 3. Divide by 3. X squared equals 0. Square root both sides. And no matter what, x equals 0 still. Again, this is a partition number. This is a critical number. Okay, that step's easy. Take the derivative, set it equal to solve for x. Step 2, create your number line. For which values of x is the original function increasing or decreasing? Create your sign chart and plot our critical number, our partition number. So that's what we'll do here. Here's my number line. There's negative infinity. There's positive infinity. And there's 0, my partition number, my critical number. Now make your intervals. Negative infinity to 0, 0 to infinity. These are my intervals. And now you pick test numbers. From negative infinity to 0, you can pick negative 1,000, negative 1,000,000, or how about just negative 1. From 0 to infinity, same thing. 100, 1,000,000, 5,000,000, 3,000,000. It doesn't matter what number you pick because all I'm worried about is the sign that comes out. So from 0 to infinity, I'm just going to pick 1. This is a sign chart for the first derivative. So plug these numbers into the first derivative. Oops, scroll up a bit. So f prime of negative 1, f prime of 1, 3 times negative 1 squared, 3 times 1 squared gives me 3, gives me 3. Okay, so let's look at the first one, and you get a positive 3. It is a positive number, which means from negative infinity to 0, the first derivative is positive, which means the original function will increase. Look at the second number. It is also positive, meaning the first derivative is positive from 0 to infinity, which means the original function will increase. Okay, cool. So we increase on all the intervals. So there is a f of x increases on negative infinity, basically to infinity. Now let's draw. Again, I'm going to rewrite the function 1 plus x cubed over here. Okay. So over here, let's just get some information out of this. X-intercept, you let f of x equal 0. This means 1 plus x cubed equals 0. Move the 1 over, and then cube root both sides. And we'll get x equals negative 1. There is my x-intercept at negative 1, 0. Okay. Let's say you wanted a little more information. I didn't do it on the last one, but you can still do it on the other ones. Let's say you wanted to find the y-intercept. To find a y-intercept, you let x equal 0. Okay, so let's see, why is that taking a while? X cubed equal to, still recording. Let me see what happened. Yep, lost connection on my laptop. So I'm gonna pause this for a moment. Okay, we're back. I don't know what happened. I had to restart my laptop. Great. Okay. So where we left off, we were finding the x-intercept. So I take the original equation, set it equal to 0, solve for x, cube root both sides, I get negative 1, 0. And like I said, I'm going to find the y-intercept. I didn't do it on the last problem, but the y-intercept could give us more information on how to actually sketch the sketch a little better. So for y-intercept, you let x equal 0. So with that being said, I get f of 0 equal to 1 plus 0 cubed, and we end up with 1, which means I get a y-intercept at 0, 1. Okay, now we have all the pieces we need. Let's go ahead and graph this using the x-intercepts, y-intercepts, and the sign chart above. Okay. Let's see. Green, good. Okay, I'm going to plot the x-intercept at negative 1, 0, so right there. Y-intercept at 0, 1, right there. And now let's follow the sign chart. So from negative infinity to 0, the function is increasing. So the original function is increasing. So it should look something like this. And then from the sign chart again, from 0 to infinity, we increase again. So something like that. That's it. All right. Kind of curves around a bit. Oh yeah, and on the problems it says add a horizontal tangent line. Well, we have a horizontal tangent at 0, so there would be a horizontal tangent line right there, where m equals 0. If I went back to the other problem, my horizontal tangent line would be at 4. So I would have a horizontal tangent line right here. Okay. Okay, cool. All right, there's that. And now we get into the definition of local extrema. And extrema is just a fancy word for maximums and minimums. So if you see the word extrema, this means look for a max, look for a min. Okay, first definition is looking for a local maximum. This means that your graph must go from rising to falling as shown below. We see that our graph rises and then falls, and you see that the point right here would be a maximum. It is a high point. So the graph must rise and then fall. So that's what a local maximum is. So I'll just erase that. There you go. And then if you're looking for a local minimum, well, the graph must fall and then rise, decrease and then increase, as you see here. Our graph decreases and then increases, creating a local minimum at the bottom. So that's just the local minimum. It must go from decrease to increase, from falling to rising. Okay. And let's see, 3, a local extremum. F of C is called a local extremum if it is either a local max or a local min. So this means that we will find maxes or minimums at critical numbers. And where we find these local maxes and mins, they will also occur at turning points. What it means to have a turning point means the graph changes direction. So if I just drew a little graph here, and let me see, here's my graph. Well, this would be a maximum and would also be a turning point because the graph goes from rising to falling. That's why it would be a turning point. Same thing here. Down here, this minimum would be the low point, a local minimum, and it also would be a turning point because we go from decrease to increase. So that would also be a turning point. Turning point means the graph has to change direction. And normally, those maxes and mins are found at the critical numbers. Okay, I can leave that graph up there. All right. Turning point means to change direction, right? Graph changes direction. Or graph goes from increase to decrease, decrease to increase. I think we'll see that on the next page. Yep, here's our sign chart. So a theorem for local extremum for max and mins and critical numbers. If f of c is a local extremum, so if f of c is a max or minimum, then c is a critical number. To find local extrema, we must find all critical numbers, test one to see if it produces a local max or min or neither. And the way we do that is by what we've been doing already. We've been creating sign charts. So here we have a local minimum if the graph goes from decrease, if the graph goes from decrease to increase, then C would be a local minimum. Let me make that better. C would be a minimum, okay? That would be a min. Down below, if you go from increase to decrease, then C would be considered a local max. You see how the graph changes directions. Decrease, increase, C would be a local min and a turning point. Or increase to decrease, C would be a max and a local turning point. Now, if nothing happens, if our graph goes increase to increase, there is no turning point and there is no max or min. So if our graph goes increase to increase, then C is nothing. C is neither. C means nothing to us. Okay? Same thing, decrease to decrease, nothing. C is nothing to us. Okay, awesome. So that's how we look for max or mins. We do it based on the sign chart. So let's keep going. All right, 3, locating local extrema. All right, find the critical numbers of f. That's our first step. So find critical numbers, find partition numbers, take the first derivative, set it equal to 0, and solve for x. That's it. See how easy that is? So let's do that. Am I crazy? Yes, I'm crazy. I'm stuck at home. What else do you expect me to do? Now you're making me do math. You know all mathematicians go crazy, right? All right, back to work. So take the derivative, 3x squared minus 12x plus 9. Set the derivative equal to 0. 3x squared minus 12x plus 9 equal to 0. We see that this has a greatest common factor of 3. So divide by 3, divide by 3, divide by 3, divide by 3. We get x squared minus 4x plus 3 equal to 0. So I could have factored out the 3 and then divided, but why not? Since it's an equation, why not just divide everything by 3? Just get it over with. Okay, and now we will factor this and find our critical points, our critical numbers. And this factors to x minus 1, x minus 3 equal to 0. So the only factors of 3 that can make 4 are 1 and 3. And our critical numbers are going to be x equals 1 and x equals 3. These are critical numbers or partition numbers, either one. Okay, so just like all the other steps, we now go down and make a sign chart. So that's our next step. We make a sign chart. Okay, so make a sign chart. Here's negative infinity. Here's positive infinity. Plot our critical numbers. Here is 1. There is 3. Now make your intervals. Negative infinity to 1. 1 to 3. 3 to infinity. These are my intervals. All right, hang on. Nope. Somebody joined in left. Okay, now you pick test numbers. And we'll do that down below. From negative infinity to 1, we're going to pick 0. From 1 to 3. I'm thinking of a number between 1 and 3. 2.5, perfect. Just kidding, 2. And then 3 to infinity, we pick 4. Remember, this is a sign chart for the first derivative. So plug all of these into the first derivative. F prime of 0, F prime of 2, F prime of 4. Okay, and I'm not going to write it all down. I have my calculator with me, so I'm going to use the first derivative above, 3x squared minus 12x plus 9, and plug in all these numbers. 3x squared plus minus 12x plus 9. Enter. Now if I plug in 0, I get 9. So I'm coming out here. I get 9. If I plug in 2, I get negative 3. If I plug in 4, I get 9. Okay. Again, we don't really care what the number is. We just care about the sign. So look at 9. This is positive, which means looking at the sign chart, from negative infinity to 1, the first derivative is positive, which means the original function will increase. Look at the second number, negative 3. That is negative. This means on the interval 1 to 3, the first derivative is negative, and we will decrease. And then the last number, 9, positive. From 3 to infinity, the first derivative is positive, which means we increase. Okay, but we're not done. Let me see. Find local max and mins. So step B is almost done. I should have put some more room over here. So now, based on our sign chart, we want to find max and mins. So look at critical number of 1. At 1, we increase and we decrease. So if we increase and decrease, this means that 1, x equals 1, is a max. X equals 1 is a max. Okay, then look at 3. At 3, we decrease, and then we increase. If we decrease and increase at 3, this means that x equals 3 is a minimum. Not done. We want to find the exact point of these max and mins. So take these values and plug into f of x, because these are x values, and now we want y values. And the reason we plug it into f of x is because we're graphing f of x. We are graphing f of x based on all the characteristics of the first derivative. So 1 and 3 are critical numbers. Now 1 and 3 will create a max and min. Now we need to find the exact location of that max and min. So take 1, take 3, plug them into the original function. So f of 1 and f of 3. And I'm going to go look at my original function. There it is. I'm going to do this on my calculator. X cubed minus 6x squared plus 9x plus 1. And I'm going to type in those numbers. If I type in 1, I should get 5. Let me see. 1 minus x negative 5 plus 1. Yep, that's 5. Okay. So f of 1 gives me 5. If I type in 3, I get 1. What this means is that 1, 5 is going to be our max. 3, 1 is going to be our minimum. Now we're ready to sketch. Okay. Let's see what points I have. Let me rewrite the original function down here. X cubed minus 6x squared plus 9x plus 1. Let's see if I can do that from up here. Plus 1. Okay, so now come down here. Let's do some work. Like I said, let's get some X-intercepts and Y-intercepts. So for X-intercepts, you let the function you let f of x equal 0. So you take x cubed minus 6x squared plus 9x plus 1, set it equal to 0. But I'm going to tell you what, this doesn't factor. It doesn't even factor by grouping. So we're going to say too hard. And move on to the Y-intercept. You like that one, huh? Then let's go for the Y-intercept. This is always the easiest one to find. Plug in 0 for x, and you'll get 0, 0, 0, 1. I won't even do that yet. Hang on. Don't type 1. There you go. I'll be left with 1, which means my Y-intercept is 0, 1. There we go. All right. So let's go ahead and plot. I am going to use my Y-intercept at 0, 1. I'm going to plot my max at 1, 5. 1, 1, 2, 3, 4, 5. And I'm going to plot my minimum at 3, 1. 1, 2, 3, 3, 1. There we go. Now let's follow our sign chart. Okay. My sign chart above says from negative infinity to 1, our graph is going to increase. So this is what we should look like. Come on. Maybe a little more curvier because you have to curve around. And then the graph says from 1 to 3, we are going to decrease. And then it says from 3 to infinity, the graph again is going to increase. So that is what we're looking at. Let me label these down here. 1, 2, 3. 1, 2, 3, 4, 5. So here's increase, here's decrease, there's increase. There you go. Just like the sign chart says, increase, decrease, increase. Could I put that on that one? Yes, I could have. So on the first one, that's increase, just like the sign chart says. Okay, cool. Almost there. Number 3, same exact process. Let's do it. Okay, so we want to graph the original function. So let's find the critical numbers first. Take the derivative, set it equal to solve for x. Find your critical numbers, make your sign chart, find your max and min, then let's plot. So here we go, speed run. Okay. F prime of x equals negative 4x cubed plus 100x. Perfect. There's the derivative. Now set it equal to 0. Negative 4x cubed plus 100x equal to 0. Greatest common factor of negative 4x. So I'm going to take out a negative 4x. That leaves me with x squared minus 25 equal to 0. And then solve for x. Set both terms equal to 0. Negative 4x equals 0. X squared minus 25 equal to 0. Here, x equals 0. And here, x squared equals 25. Square root both sides, x equals plus or minus 5. Remember, when you square root, you should always have plus or minus. These, again, are our critical numbers. Now let's plot them on the number line below. So this time I'll do more space. So here's my number line. There's negative infinity, there's infinity, and then I have -5, 0, 5. Intervals, negative infinity to -5, -5 to 0, 0 to 5, 5 to infinity. Okay, now pick your, nope, stop it. Too close to the edge. Now pick your test numbers. And here we're gonna have 4 test numbers, yeehaw. X equals, X equals, X equals. So for the first, negative infinity, -5, -6, -5 to 0, we'll pick -1, 0 to 5, we pick 1, 5 to infinity, we pick 6. And where do we plug these into? The first derivative. So f prime of -6, f prime of -1, f prime of 1, f prime of 6. Okay. Let me find my first derivative so I can plug these in. I'm gonna type this in my calculator. -4x cubed plus 100x. And if I type in -6, I get -264. This, just type them all in first. Hang on. -1, -96, 1, 96, and then +264. Right? Or did I mess that up? Oh, wait. Yep, I didn't type in 6 in the beginning. -6, that gives me a +264. There you go. -6, 264, -96, 1, 96, 6, -264. Okay, let's look at our numbers. Very first one is positive. So from -infinity to -5, positive increase. Next number is negative. -5 to 0, negative decrease. Next is positive. 0 to 5, positive increase. And then last one is negative. So negative and decrease. There you go. Almost done. Let's look at our numbers. First number up is -5. You increase, and then you decrease on -5. This means that x equals -5 is a max. Then we look at 0. We decrease and then increase. This means that x equals 0 is a min. Last number is 5. We increase and then we decrease, which means x equals 5 is max. Okay, we're not done because now we need to find the exact points of the max and min. So what do? We plug them into the original function. That is correct. Okay, so plug into f of x. Okay. So make this little squiggles here, and f of -5, f of 0, f of 5. Now I'm going back up to see the original function. I'm typing all this in my calculator. -x to the 4th plus 50x squared. Enter, enter, enter. Going back to my values, and if I type in -5, I get 625. 0 should give me 0, and -5, actually 5, should give me 625. Okay. Then what this means is that at -5, 625, we have a max. 0, 0, we have a min. 5, 625, max. There we go. Okay. Let's plot. Let's see what we need. Okay. Again, I'm going to write the original function. Let's see what x-intercepts I can possibly get out of this. F of x equals -x to the 4th plus 50x squared. Okay, let's look for x-intercepts. Same exact process. Let y equal 0. -x to the 4th plus 50x squared equal to 0. I can take out a -x squared. That leaves me with x squared minus 50 equal to 0. And then set these equal to 0. -x squared equals 0. X squared minus 50 equal to 0. Here, x squared equals 0, and x equals 0. Gives you square root, same thing. Over here, x squared equals 50, square root, and in my calculator, I get 5 square root of 2, or 7.07. So x equals plus or minus 7.07, or 7.1. These are my x-intercepts. So I'll write that. 0, 0, 7.1, and 0, -7.1, and 0. Okay, if you try the y-intercept on this, you're just going to get 0. Take my word for it. Okay. Now let's plot. I'm going to plot my x-intercepts first. So 0, 0, that's not 0, 0. 0, 0, and then 7.1. I'm just going to put it on 7. Doesn't have to be perfect. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Wow, not down there. 1, 2, 3, 4, 7. There we go. Those are my x-intercepts. And now I'm going to plot my max and mins. I believe above says -5 and 625. So let me mark up my x-axis. We can make this 100, 200, 300, 400, 500, 600, 700. There we go. Back to this. So -5 and 625. 1, 2, 3, 4, 5, and then 625. Somewhere around there. 0, 0. Hey, that's already plotted. And then 1, 2, 3, 4, 5, and 625. There's that. And now let's follow our sign chart, which says from negative infinity to negative 5, we are increasing. Wait, let me write this down. Negative 505, okay, let's continue. So from negative infinity to negative 5, we are increasing. This is what it looks like. And then our sign chart says from negative 5 to 0, we are decreasing. And then from 0 to 5, that's not where 5 goes. Sorry. That's where 5 goes. From 0 to 5, we increase. And then 5 to infinity, we decrease. That's it. And ladies and gentlemen, that's how you draw the letter M. Also, if you want to know where you had horizontal tangents at, they would be right here, here, and there. That's where your horizontal tangents would be. Because at those points is where the slope is 0. So to represent increase, decrease, constant, increase, decrease, constant. Cool, huh? All right. That was it. I just wanted to sketch, right? Yep. Okay. So you see how a bunch of algebra is involved. I know you kids are great at algebra. And now you get to stay home and practice algebra every single day. Yeah. Sorry if I'm getting ridiculous. Okay. Example 5, we're just sketching a graph based off the sign chart in the given values. So first thing, let's go ahead and plot these X and Y values that it's giving us. This is an XY chart, just sideways. Okay, so let's plot those. All right. -2, -1 goes there. -1, 1 goes there. 0, 2 right there. 1, 3 goes there. 2, 1 right there. And this is almost done. Now, since we plotted all the points, just follow the sign chart above. From negative infinity to -1, the graph is increasing. So here is, let me label stuff on here. Do that, do that. That was -2, -1, 0, 1, 2. Okay, and then it says from negative infinity to -1, we are increasing. So there's that. And then from -1 to 1, we are still increasing. And then from 1 to infinity, we decrease. So curve around and down. Super ugly, but you see what's going on. Again, to represent the sign chart, here's increase, there's decrease. And this could also be constant. So gross. So constant. And there it is, children. That is it. Okay. Let's see, bottom one, intercepts and local extrema, another theorem. If you have a polynomial of degree 1 or higher, then you will have at most n x-intercepts and n-1 local extrema. So if I wanted to explain that real fast, if my polynomial was x to the fourth, this means I would have 4 x-intercepts and 3 extrema. That's all that means. So if my degree is 4, I should possibly have 4 x-intercepts, and I should possibly have 3 max or mins, 3 maxes, 3 mins, or 3 max and mins. And there you go. That is it. See y'all later.